G'day everyone, it's DB93 here again. Today I'd like to talk about gravity and how that would pertain to straight level flight on both a flat and a globe Earth. Now we'll start with gravity, but what we need to talk about first is what we observe and why we observe it. I've been on the flat Earth community through comment sections, videos, both for and against, and what I've noticed is a lot of flat earthers talk about gravity as density. So because this pen is heavier than air, it falls. And they say that that's due to density. Technically, yes, but it's not the only thing going on. So the key question that people aren't asking is, why is it falling down? Okay? Why does something sink towards the earth? Why doesn't it sink left or right? Why doesn't something heavier than air go up and something lighter than air go down? So we need to answer this question. And we can explain it, and there's actual experiments we can do to examine it. And that's what this video will be on, mainly. So we'll start with a few hypotheticals. If I am hanging a ping pong ball, right, say the pen's a ping pong ball, from a string, and I suddenly accelerate left, the inertia of that ping pong ball will drag it behind. Does the same thing happen with a helium balloon? Because as we know, the ping pong ball will sink in air, whereas a helium balloon floats. So do we see the same thing? The answer is yes. So on a vertical plane, we have something floating up and something sinking down. Alright? But on a horizontal plane, we see the exact same motion. Why do we see that? Because based on what we would understand is that things would operate similar on either plane, vertical or horizontal, but that's not what we see. And the reason for that is on the horizontal plane, there is a downwards acceleration force, not only on the items in question, but also the media that surrounds it, and in this case that is atmosphere. And that acceleration is due to gravity. But on the horizontal plane, we don't have acceleration going either way, and we're only moving the item rather than the media surrounding it as well. So how can we test this? Well, what we can do is we can have a sealed container, and that'll seal in the environment. Now if we have a sealed container and we accelerate it in the horizontal plane, what will we see? If something is floating in that container, what will it do? Will it again lag due to inertia, or will it perhaps lean in towards the direction that it's being accelerated? Because logic would suggest that, a certain logic would suggest that it stays where it is, and then when you move it, its inertia will drag it behind no matter what. So I've actually gone ahead and done this experiment using a large container, some water, a ping pong ball, and I didn't have any string, so I used a gator clip, but it still has the same sort of effect. And you can see this here. Okay, so here we've got a closed system. Inside is water, and then we've got a ping pong ball, which is lighter than water. So in comparison, you've got air and you've got your helium balloon. When I accelerate this way, what do we expect is going to happen? Is the ping pong ball going to lean this way due to inertia? Well, let's have a look. Now, as I explained, and as you saw, when you accelerate it, it leans forward. The reason it does this is you need to understand that the Newton's equation for force is equal to mass times acceleration. So everything in that system has the same acceleration. The only difference is the mass. So the water, which has a larger mass, will thus have a larger force acting on it, and thus more energy than the ping pong ball does. So what happens is that increased energy will make it get ahead of the ping pong ball, get underneath it, and push it away. And that's why we see it moving. Now, I understand some of you may be thinking, well, if I'm accelerating it to the left, shouldn't the force be acting in that direction? And that's a pretty solid no. We can observe that when you accelerate in a car. So when you accelerate in a car, your inertia will push you back into your seat, and that will be an acceleration force towards the seat. We know that when you push it that way, everything will accelerate towards that wall. And that'll be relative to the situation inside. So, although you're accelerating the container, everything in it doesn't know what's going on. And so its inertia will hold it where it is, and effectively accelerate towards that wall. So it can be a little tricky to get your head around, but if you think about it, it does make sense. You can see from here that, you know, there's the direction in which density affects things is due to acceleration. Okay? Now what happens if there's no acceleration? Well, we can see that in this example as well. Because there's no horizontal acceleration, it's not going one way or the other. And if there was no vertical acceleration, we can see that as well. We would see that as well, I should say. The fact that we see things, that it's actually floating in the water, means there is an acceleration force present. And that acceleration force isn't described by density. It is described by gravity. So that is definitive proof that there is something there acting, and we know it currently as gravity. So another question I see a lot is, how can a magnet lift up a paperclip off the earth, and yet the same force holds in millions of gallons of water to the Earth's surface? And again, that comes down to Newton's equation of force. Force is equal to mass times acceleration. So there is constant acceleration due to gravity. Now, if you have 1,000,000 litres of water, that'll weigh 1,000,000 kilograms. And let's say that we'll round the gravitational force up to 10 meters per second acceleration. So you've got 1,000,000 times 10. So you get 10 million newtons of force holding that water to the earth. Whereas if you've got a 2 gram paperclip, that is 0.002 kilograms multiplied by the 10, which is 0.02 newtons. So you can see that there is a very big difference in force compared to the water and the paperclip. And the larger the mass is, the more scaled up that force is, because acceleration is a constant. So the magnet doesn't actually need a lot of force to lift that paperclip off of the Earth to defy gravity. And that's why we see that. And that's how the ocean's actually held in place. Now, how does this pertain to straight and level flight? Well, we'll use this because I don't have any large enough balls to where I live to do this, and I couldn't be bothered going out and buying a basketball or something like that, or a soccer ball. We'll use this lid as a 2D representation of the globe. Now, if you've got your plane, it should fly like this during straight and level flight. But a lot of flat earthers say that you can't do that without dipping the nose, like so. That makes sense. But what you're not accounting for is that of how gravity affects the plane as it goes around the globe. And what I mean by that is there's people whose job consists entirely of making sure that aircraft are loaded so the center of mass is at the same point of the point of lift. Now, this pen's accelerating downward, and my finger is pushing it back up to hold it in place. It's doing so at the center of mass, so it's sitting level. Now, if it came across here, it would look like, from this point onward, that the nose was starting to tilt up away from the Earth. So like so. Now, gravity would still be pointing perpendicular to the Earth, straight down towards the center of mass. And so, it would level out. Okay? Always level out. So the plane will actually automatically adjust gradually and consistently as it goes around the curved surface of the Earth, making straight and level flight possible without the need for conscious or automatic correction. Right? You don't need any electronics, you don't need human adjustment. It automatically does it due to the center of mass and how it interacts with gravity. So just to recap, we've shown that gravity is actually an acceleration, and it only creates a force once it interacts with mass. We've experimentally proven that and shown how it would act on a horizontal plane and how that gives things direction based on its density. And we've shown that straight level flight is possible with the globe Earth. But if you think about it, on a flat Earth, now you need to ask why it's heading straight down. Now, the current idea of where gravity is attracted to is the center of mass. Now, if not the center of mass, then where? And if you've got an idea, please mention it in the comments, and I'm happy to discuss it with you, and whether it would be possible or not. And we can talk about it. And if you come up with something convincing, I'll give you a shout out in the next video. Now, you've got your flat Earth, and the center of gravity should be right here, in the middle. So if you're out on this edge, and you've probably seen this model before, you'd be pointed in. What that means for aircraft flying around the edge of the flat Earth, you'd be flying nearly with your wings at a vertical, just to create lift against the point of gravity, pulling you back towards the center. Problem is, we don't see that. I live in Australia, and I've never seen aircraft flying on an angle like that. They always fly flat. We know that straight level flight is possible on a globe Earth. I have my doubts whether it's possible on a flat Earth, based on what we've just observed with gravity, because we've observed that it's due to acceleration and the vector associated with it. Now, if you have any questions, feel free to leave a comment or email me at db93science@gmail.com. And I'm happy to talk to you about it. I'm happy to debate with you. If you got ideas, I'm happy to listen to them. If you think I'm wrong, let me know. And if you're right, I'll give you a shout out in the next video, and I'll explain to everyone how I was wrong, and I'll explain the corrections and what that means compared to the two models. So I look forward to seeing replies, and I'll catch you next time.